exploring the groundwater systems of the Central Valley with Earth Imaging Technologies, brought to you by the Environmental Geophysics Group at Stanford, with funding from the Gordon and Betty Moore Foundation. The Central Valley of California is one of the most productive agricultural regions in the world. While much of the irrigation water to support this agriculture is surface water, originating as snowmelt, the groundwater of the valley is also a critical source of water for irrigation. But the water levels in the groundwater systems are declining, indicating the need for new approaches to sustainable groundwater management. And for that, we need an improved understanding of the functioning of the groundwater systems. How can we use data acquired with Earth imaging technologies, satellite, and geophysical systems? Let's first use satellite data to consider what is driving the demand for groundwater. In the winter months of November to March, rain falls in the valley. Satellite data provide a measure of precipitation and show the stark difference between the drier southern half of the valley and the wetter northern half. The dominant red color in the south corresponds to approximately 300 millimeters or 11 inches of rain per year, while the blue color shows more than twice that amount, falling in the north. Throughout the winter, while rain falls in the valley, snow accumulates in the Sierras along the eastern edge of the valley. The more snow there is in the Sierras in the winter, the more surface water there will be in the valley in the spring and summer for irrigation, and the less demand there will be for groundwater. Here we can use another form of satellite data to map out the thickness of the snow and predict the demand for groundwater. And what we see, again, less water, this time stored as snow, in the Sierras adjacent to the southern part of the valley. In the spring, the snow melts and fills the reservoirs with water. Shown here by the size of the blue circles is the mean amount of water stored in each of the reservoirs over the past 20 years. There is much more available water stored in the reservoirs in the north. In the late spring and summer, water from the reservoirs is delivered to the valley for the growing season through a network of rivers and irrigation canals. As we move into the summer season, if there is insufficient delivered surface water, growers turn to the pumping of groundwater to meet their irrigation needs. The result? There is more pumping of groundwater in the warmer, drier south. We now have a remarkable Earth imaging technology that provides key insights into the functioning of a groundwater system. We have satellite measurements made every 6 to 12 days, referred to as INSAR data, that display the consequences of groundwater pumping, the subsidence of the ground surface that occurs when groundwater is withdrawn, with the color scale shown here going from blue to red as the amount of subsidence increases. And now the disparity between north and south in terms of available water shows up as greater subsidence in the south, where more pumping of groundwater is needed to compensate for the lack of surface water. This image shows the 1.3 meters, or 4.5 feet, of subsidence that occurred in just under 5 years between January 2015 and September 2019. So the ground is sinking in places about 26 centimeters, or 10 inches per year, due to the extensive pumping of groundwater. There is so much we can learn from these Earth imaging satellite data. They monitor changes at the ground surface linked to the dynamics of the groundwater system. But to truly understand what's happening in the groundwater system, we need to see below the surface. And to do that, we focused on part of the subsidence bowl and acquired data using another remarkable Earth imaging technology, an airborne electromagnetic system, a geophysical system, carried by a helicopter. The white lines that you're seeing are the flight lines that we flew, a total of about 800 kilometers or 500 miles. Using the geophysical system in this study, SkyTem, allowed us to image about 350 meters or 1,000 feet below the ground surface. The data that we acquired will be shown here above the Google Earth image, but are actually measurements made below the ground surface. We mapped out the electrical resistivity and can use those measurements to obtain images displaying the types of geological materials that are present and how they are distributed. What you are seeing now is called a fence diagram, a collection of 2D slices into the ground, showing what is present from the ground surface down to 350 meters or 1,000 feet below the ground surface. Along the mountain front, the pink shows the bedrock of the Sierras that extends below the valley's sediments. The red, orange, and yellow colors, farther out in the valley, show where there are the sands and gravels, which hold large amounts of water that can flow easily and be pumped to the surface for irrigation and domestic water use. In blue are the clays that act as impediments to flow. Green indicates the presence of silt, or the fine interlayering of sand and clay. When clay is interspersed within the thick zones of sand and gravel from which groundwater is being pumped, it's the pulling of water from the clays that causes most of the subsidence that we see. So mapping out the clay-rich zones is essential for understanding what areas are at risk of subsiding. Some of the other important features we can resolve: we can see where there are interconnected pathways of sand and gravel that can act as fast paths to efficiently move water from the surface to deep within the valley to refill, recharge the groundwater system with water. Groundwater in the Central Valley is essential for our food supply, essential for domestic use, essential for the functioning of natural ecosystems. Pulling together all of these data acquired using Earth imaging technologies, the satellites, and the geophysical system is helping us better understand the complex spatial and temporal interactions between snowfall, rainfall, groundwater throughout the year in the Central Valley. Huge thanks from us at Stanford to those who made data available and assisted in data acquisition and processing, and thanks to the Gordon and Betty Moore Foundation for supporting our efforts to advance the adoption of Earth imaging technologies as the basis for groundwater science and groundwater management.